Okay, number 11. Use the quotient remainder theorem with a divisor of 2 to prove the following statement. The square of any integer can be written in one of two forms, 4 times an integer or 4 times an integer plus 1. So if you square any integer, it's either a multiple of 4 or 1 bigger than a multiple of 4. So this beginning part, use the quotient remainder theorem with a divisor of 2, that's saying that when you divide any integer by 2, you either have a remainder of 0 or a remainder of 1, right? So you divide by 2 and either your remainder is 0 or your remainder is 1. So we start by supposing we have any integer. Suppose n is an integer. All right, so n could be even or n could be odd. That's what the quotient remainder theorem with a divisor of 2 says. It says that when you divide by 2, you either have a remainder of 0, which means the number was even, or you have a remainder of 1, which means the number was odd. So let's suppose n is an integer, and we're going to divide this into cases. Case 1, n is even. Okay, so these are our cases because they told us to use the quotient remainder theorem with divisor equal to 2. So when the divisor is 2, there are two cases. Either the remainder is 0, in which case n is even, or the remainder is 1, in which case n is odd. So we have two cases, n is even and n is odd. So if n is even, then n equals 2k for some k in z. Thus, n squared, the square of my integer, would be 2k squared, which is 4k squared. Since k squared is an integer, n squared is a multiple of 4. And that is what we were trying to show. All right, we were trying to show that the square of any integer is either a multiple of 4 or a multiple of 4 plus 1. Okay, so we supposed n was an integer, and then case 1 is that n is an even integer, and we get that it's n squared must be a multiple of 4. Okay, case 2, n is odd. Then n is 2k plus 1 for some k in z. Thus, n squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is 4 times k squared plus k plus 1. Since k squared plus k is an integer, n squared is a multiple of 4 plus 1, which is what we were trying to prove. That's the other case, that it's 4k plus 1, 4 times an integer plus 1. So in case 1, you get 4 times an integer, and in case 2, you get 4 times an integer plus 1. Number 12, prove or disprove for every integer n, n squared minus 2 is not divisible by 4. So let's do a couple of tests. Choose a random integer, n equals 8. Okay, so n squared minus 2 would be 64 minus 2, which is 62, and that is not divisible by 4. Seems true there. Pick another integer, n equals, that was an even number. Let's try an odd number. Let's try n equals 11. So n squared minus 2 would be 121 minus 2, which is 119, which is not divisible by 4, right? Okay, I'm pretty convinced that this is true. You could try a couple more, but I think that this is true. I'm going to try to prove it. Okay, so for every integer n squared minus 2 is not divisible by 4. So it's hard to prove something's not divisible by 4, right? Proving a negative is tricky. So what we're going to do here is a proof by contradiction. We're going to say suppose not. So we're going to suppose that this is not true and try to derive a contradiction. Okay, so the negation of this statement says that we would suppose there exists an integer such that n squared minus 2 is divisible by 4. So you suppose that the statement is not true. So you suppose the negation of the statement. Suppose that there is an integer so that n squared minus 2 is divisible by 4. All right, so if we're supposing that there is an integer n such that n squared minus 2 is divisible by 4, then we know n squared minus 2 equals 4k for some k and z. Okay, so we know that n squared minus 2 is a multiple of 4 because we are supposing that that is true. All right, now my last problem dealt with n squared and multiples of 4, and it used cases where we let n be even and we let n be odd, the two cases, n is even and n is odd. So I think that I'm going to do that again because this has so many similarities. It's got the n squared and it's got the divisible by 4 part. So let's do that. Let's say case 1, n is even. Then n is 2j for some j and z. Thus, n squared minus 2 is equal to 2j squared minus 2, which is 4j squared minus 2, which we know from our earlier assumption, right, that n squared minus 2 is divisible by 4 has to equal 4k. Okay, so now I'm just going to look at these last two statements in this chain of equality, and I am going to manipulate that equation a little bit. So I would say thus, I'm just gonna move the 2 to the right and the 4k to the left. So add 2 to both sides, subtract 4k to both sides, and we have 4j squared minus 4k equals 2. Now, dividing both sides by 4, yields j squared minus k equals a half. And I've reached my contradiction because j squared minus 4 has to be an integer. J and k are both integers. Squares and sums and differences of integers are also integers, but I have j squared minus k as a half, which is not an integer. So I've reached my contradiction. Common symbol for contradiction is 2 arrows facing each other. And I just have to write one last sentence to explain. Okay. Since j squared minus k is an integer, we have reached a contradiction So our supposition must be false. So that's case 1. Okay. And if our supposition is false, that there exists an n in Z such that n squared minus 2 is divisible by 4, then its negation is true, which is what we were originally trying to prove. That for all n in Z, n squared minus 2 is not divisible by 4. Okay, so by proving that the negation is false, it has to be that the original statement is true. Now, we've only shown it for one case here, that when n is even, this works. Now let's see what happens when we do n is odd. Case 2, n is odd. Then n is equal to 2m plus 1 for some m in Z. Thus, n squared minus 2 equals 2m plus 1 squared minus 2, which is 4m squared plus 4m plus 1 minus 2, which is 4m squared plus 4m minus 1, which from our original supposition is supposed to be a multiple of 4, equals 4k. Thus, 4m squared plus 4m minus 4k equals 1. So I've just moved the 4k to this side by subtracting it from both sides, and I added 1 to both sides to move the 1 over there. Now, dividing both sides by 4 yields m squared plus m minus k equals 1/4. And again, we have reached a contradiction. M squared plus m minus k has to be an integer, so it can't be 1/4. So just one final sentence to explain the contradiction says, since m squared plus m minus k is an integer, we have reached a contradiction. And thus, our supposition, our original supposition, is false. Therefore, the statement to be proved is true.